Hello everybody, this is Dr. Jacob from Jacob's Lab with another video for your educational purpose. Today I will be talking about work I did at Mallinckrodt and Petrolite during the years 1988 through 1991. The work was initially started at Petrolite and continued at Mallinckrodt. So basically, we were interested in making alpha-chloro beta-gamma unsaturated ketones at esters starting from the fully substituted unsaturated ketones. The reason these were interesting is that we were using it for making water-soluble corrosion inhibitors of the alpha-chloro unsaturated esters and ketones with the sulfur and nitrogen nucleophiles. However, the work I am talking about is the general way to make these reactions work. In other words, how to make the unsaturated alpha-chloro beta unsaturated ketones, how to synthesize it, and its novel reactions. So let me show you the ways in which there are two ways in which we made these fully substituted unsaturated ketones. And the first one is by electrophilic addition of acid chloride to substituted olefins, as shown here in this slide. It's a kind of a Friedel-Crafts electrophilic substitution on a vinyl compound. It's almost like a Friedel-Crafts using tin chloride. This goes in reasonable yield, and the workup involves quenching with KOH and ethanol to basically make it neutral because it's highly acidic and corrosive. Now, the yields are anywhere from 62 to 71%, reasonably good yield for this type of reactions. And these unsaturated ketones, you can have R and R1 methyls and ethyls, and same thing with R2 and R3. It could be hydrogen or methyl ethyl or even cyclic, as shown in the last one here. You can see that these could be cyclic. In other words, this could be tied up as the cyclic counterpart, okay? And this R1, this R1, R2 and R3, this could be a cyclic or different R groups here. So that gives a general reaction pathway to this. Now, the other one is, the other way to make it is using unsaturated ketones, alpha-beta unsaturated ketones from mesithyl oxide. So you know mesithyl oxide can be made from acetone. Condensation of acetone gives mesithyl oxide. It can be commercially obtainable from many chemical companies in kilogram quantities. So using this mesithyl oxide, we use this procedure in the literature where you make the anion using sodium amide in THF, and the anion is alkylated with RX. RX could be different R's, as you can see here, and X could be the halides. Now, what happens is the strong base sodium amide deprotonates the beta methyl group, and it forms deconjugated to this carbon anion is formed here. So that enolate alkylates with R to give the product. Now, initially it is a beta-gamma unsaturated ester. Now, this tosic acid, catalytic amine, it shifts it back to the unsaturated ketones. So here you have another way to make the fully substituted unsaturated ketones. Now, the way we made the alpha-chloro esters, in other ketones, in this case the ketones, in other words, from the fully substituted ketones, unsaturated ketones, we use hypochlorous acid to give the alpha-chloro product using the procedure of Dr. Wolensky at Purdue. He did this work in the early 80s. He made alpha-chloro halides of vinylic halides of ketones, and he used it for acid catalyzed cyclization to form furans. Now, we made this for nucleophilic reactions. In other words, we wanted to use a base to do the reactions of these interesting species of compounds, allylic compounds. So we use the same procedure, that is, acetic acid is added to a solution of the ketone in methylene chloride, and calcium hypochlorite is added in situ to generate the HOCl, and that adds at 0 degrees ice cold temperatures to give the desired alpha-chloro compounds in yield ranging from 60 to 80%. Very easy to do this reaction and filtration after workup, and methylene chloride is evaporated and it's filtered through silica gel using hexane, and you get very good 95% plus pure product of the allylic halides, which is used instantly the same day it's used, because it doesn't have much shelf life if you keep it at room temperature. So these reactive species, we were interested in, as I said before, we were interested in reactions with sulfur and nitrogen nucleophiles to give the quaternary salts of these compounds. But now, as a side reaction, as a spin-off of the project, we found out that these can be used for other reactions, intramolecular reactions using base to get cyclopentenones. This was a rather serendipitous discovery, because this first time we did this was the reaction with ammonium hydroxide, and we were expecting to get quaternary salt of ammonia. However, the ammonium hydroxide resulted in the cyclopentenone. Then we realized that the alpha enolate is formed, and that attacks it to give the cyclopentenone. Now, which is why we did this by different bases, strong bases, potassium tertiary beta-oxide, LDA, potassium hexamethyl silicide, all in THF, and then phase transfer with sodium hydroxide, and finally the one I mentioned, aqueous ammonium hydroxide, which of course started the whole process. This reaction, giving the product, made us go back to all the other bases. Now, the mechanism, of course, is that in the case of bases, the anion is formed here and it attacks in SN2A to give the cyclopentenone. This reaction has not been reported. There is no, in the history of literature, there is no such reactions reported. So we had discovered a new reaction quite serendipitously, accidental discovery. We were reacted with base to intramolecular cyclization. Now, with ammonium hydroxide, that was really interesting from a commercial point of view, because all you have to do is take this and put it in 35% ammonium hydroxide water, and in 2 hours you get this product in different yields. So here, ammonium hydroxide gives almost, aqueous method E gives almost very good yield, just like the other ones. Method E gives 68% yield. So all the reactions are pretty much between 60 and 70, 75% yield. So this one was very interesting, and the mechanism that we proposed, of course, for the ammonium hydroxide reaction, we proposed a base-induced reaction with ammonium hydroxide as base. Well, the first step, we believe that the ammonium hydroxide forms an imine, or rather enamine, as you can see here, enamine. These enamines can react. If you remember, Stokes enamines react with halides to give the alkylation. Now, in this case, you see it's an SN2. The enamine can react in an SN2 prime way, attacking at the beta carbon, not at the alpha, which is impossible for the nitrogen to attack here. Now, that's a different story. But anyway, we proposed this mechanism where the imine attacks in an enamine type of reaction to give this intermediate cyclopentenone imine. Now, in water, it hydrolyzes to the ketone. So finally, we isolated this compound just by stirring it with 35% ammonium hydroxide. Very practical, commercially applicable reaction to make cyclopentenones. As you know, these cyclopentenones are very important for perfume industry and other pharmaceuticals. There are many compounds based on substituted cyclopentenones. So this pathway is quite interesting, starting from unsaturated ketones to alpha-chloro compounds. So that's the mechanism for this. And the other one, mechanism of base-induced cyclization, we can clearly propose that in this case it was a simple enone addition, SN2. But in the case of reactions of sulfur-based nucleophiles with esters, we did this reaction first with esters, unsaturated esters, alpha-chloroesters, and we found out that the anion of dithione reacts with the alpha-chloro-unsaturated esters, the alpha-chloro-unsaturated esters, to give the Claisen product. In other words, first you get a ketone by a Claisen reaction with the ester. Now this intermediate anion, it's a very strong base. I mean, it's a weak base, but this hydrogen, this is stabilized. This lithium anion is stabilized by the ketone and the sulfur. So this is a very, we found out that as soon as it is formed at very low temperature, minus 70 to minus 30, this cyclysis to give the product, to give this product. So this goes from here to here. Whereas this one, to make the ketone inlet work without sulfur here, it takes very strong base and higher temperatures. It doesn't happen at 0 degrees or lower. It happens at room temperature or reflux. So you see the difference, the sulfur and without sulfur and sulfur causes. So that is one of the mechanistic pathways that I am proposing. Now, I also want to show you the ketone enolates of cyclopentenones, as I said earlier, proceeds at low temperature. So this is a reaction of ketones. If you start with alpha chloroketones, it cyclizes at room temperature, whereas when we did the reaction with esters, the intermediate compound cyclizes instantly when you have sulfur or nitrogen stabilizing the anion. So that's what it's shown here. It's two different scenarios. One, it's very, very low temperature reaction. So obviously there is some mechanistic sulfur and nitrogen assisted reaction. This is sulfur and nitrogen assisted cyclization, because as you can see in the mechanism that I am showing here, in the first case, in the simple enolate reaction, enolate of this is formed at first. Okay, when you do the reaction, the enolate is formed first. And this enolate reacts with the allylic system in an SN2 prime. It attacks here to give the cyclopentenone with selenium. And this happens at very low temperatures. Very facile reaction. And another mechanism we are proposing, thanks to Dr. Barry Strout of Stanford University. Barry Strout proposed that it can proceed also through a vinyl cyclopropane, and he believes that sulfur and selenium assisted vinyl cyclopropane rearrangement is the most reasonable way to propose the, this is how he believes the reaction proceeds, rather than invoking an SN2 prime reaction. So in this case, according to Barry Strout, the sulfur or selenium bromide is attacked, the enolate attached to give the intermediate, which by electron shift, it's like a cone cyclization, because the selenium or sulfur can disperse the electrons towards this ring to give it towards the beta carbon of this system to give the cyclopropanone. So you got a cyclopropanone substituted by a selenium or sulfur. So it's a vinyl group also is here. This cone cyclization gives this, and this rapidly rearranges to the more stable. In other words, this is the kinetic intermediate, rapidly formed intermediate, which rapidly dissociate in the more thermodynamically more stable selenium substituted cyclopentenone. So that's the other reasonable mechanism, which is probably more acceptable, and that I will continue this presentation in the next series. This will be titled The Synthesis of Methylnomycin and Analogues using the reactions I just presented, that is the reaction to get cyclopentenones. That will be the next lecture.